Okay, hello everyone. Okay, so today we are going to go through the chapter 19 quiz. Okay, I think many of you have forgotten what you have learned previously, but I think generally there's an improvement. So all of you should keep it up, and you should really go and revise your, you should really go and revise your notes. Alright, when you are before you sit for a test. Okay, so please do so next time. Okay, so let us go through. Okay, let's start with question 1. Three bars are arranged in different order and they experience different magnetic forces between them. Now, we spoke about it previously that if there is an attraction, the only thing that you can guarantee is that one of it is a magnet. Now, what do I mean? Now, when I saw many of your answers, many of you tried to check if U was north and V was south, and then you try to see whether it is possible to figure out which poles are which. Now, this is not possible, okay, because if one of it is a magnet and the other is not, now it doesn't work. Now, sorry, give me a moment. Okay, so now what do I mean? Look at it this way. If there is an attraction between UV and WX, now the first thing that all of you will realize is that there is a repulsion between UV and YZ. This tells us that UV and YZ must be magnets. So it doesn't matter if this was south or north or south. The moment you see a repulsion, we know that this must be a magnet. Now, let us take another one, which is WX. So UV, this is a magnet. Okay, YZ, this also must be a magnet. Now, however, we see, so we know that YZ, this is definitely a magnet. Okay, but WX, you see, we see that WX over here is attracted to YZ and is also attracted to UV. However, it is important to note that because there is no repulsion evidence for WX, we cannot conclude that it's a magnet either way. Okay, I know many of you tried to say that this is north-south, south-north, but as long as there is no repulsion, okay, you cannot say that it is a magnet. Because if this was just a magnetic material, you realize that it will attract, and if this was a magnetic material, it will also attract the magnet, which is UV, right? UV, we have already said over here, is a magnet. So WX could be a magnetic material and it can attract both UV and YZ, and you cannot confirm that it is not. So therefore, only UV and YZ is a magnet. Okay, this answer is C. Okay, let's move on. A solenoid carrying a current is used to demagnetize a bar magnet. Okay, which condition achieves demagnetization? So I don't know whether you remember, the first one is in order for demagnetization to occur, it must be an alternating current. So either one of these is okay. Now, but you do not want to move the solenoid quickly, you just want to move it slowly through it. So the answer in this case is B. Now, in this case, when there is an alternating current, is to demagnetize the magnet. To magnetize a magnetic material, how do we do it? It is like this, alright? It's a coil, come down, and a direct current. This, if you put a metal inside, a metal rod inside, okay, then you will be magnetizing it. Okay, this is to magnetize. Okay, so can you please copy this diagram down? Okay, so this is to magnetize the bar magnet. Okay, next question. Okay, at any point, if you all think it's going too fast, okay, please pause the video and you can take a look at pause the video and copy down the notes. Now, if I'm going too fast, you can also replay to hear my explanation again. Now, The question 3, a piece of steel can be magnetized by stroking it with a magnet. What are poles X and Y? Now, I told you that when you stroke a magnet, this first contact point that you touch with a magnet. So for example, if this is the magnet, this is the magnetic material. If this is the north pole, you touch here, north, this point here will be north, and when you drag it over here, this point over here will be south. Okay, I say again, when you touch here, this is north, you drag it over here, here will be south. North, south, north, south. Okay, so when the magnet, okay, touches this point X over here, when the magnet north, it first starts by touching X over here and dragging it all the way over here. This point over here will be north, this point here will be south. Okay, so X will be north, Y will be south, and answer is B. Now, I don't understand why some of you chose answer A or D. Okay, there were some of you who do that. Okay, that's not possible. It cannot be that X is north, Y is south. It's not possible. Sorry, it cannot be possible that X is north and Y is also north as well, right? So in a magnet, you must always have a north pole and a south pole. Okay, so this is not possible. Neither is it possible for X to be south and Y to be south as well. So these two examples are not possible. Okay, so let's move on. Question 4. Which diagram shows the magnetic field pattern around two bar magnets? Okay, so we can see that over here, the field lines are going into the pole. So we see over here that the field lines, you see this is the arrow, they are all going into the pole. If they are going into the pole, then it must be a south pole. Now it's going into this pole, it is also going into this pole, right? So this must both be south poles. Knowing this, on the other side, it has to be a north pole. So if here is south, the other side is north, and this is how the two bar magnets are arranged. So in this case, it's NSSN. NSSN, and the answer is D. Okay. Now, 3 sheets of materials are placed below magnets as shown in the diagram, which describes the force on the material. Now, there are only 4 different types of magnetic material. Okay, the first one is iron, right? Steel, nickel, okay, and cobalt. Alright, and so since there are only 4 magnetic materials, these magnetic materials are the only materials that can experience a magnetic force when you bring a magnet close to it. If you take a magnet and you bring it close to it, if this is one of the magnetic materials, it can be attracted. Anything else will not be attracted. Okay, so in this case, the only magnetic material inside the list is iron, while aluminum and lead are not magnetic materials. So both lead and aluminum will experience no force, and iron will experience the force of attraction. So the answer is D. Okay. Now, next question, question 6. Now, figure 6.1 shows an electromagnet used in a simple door lock. When the current is switched on, the iron bolt is pulled towards the electromagnet to lock the door. When the current is switched off, the spring pulls the iron bolt away from the electromagnet, unlocking the door. Okay, so let's look at it one by one again. When the current is switched on, the iron bolt is pulled towards the electromagnet to lock the door. Okay, so when this is on, when this is switched on, the current will flow like this. Okay, and the iron bolt will be pulled towards the electromagnet. When the current is switched off, this spring, okay, will pull the iron bolt away from the electromagnet, unlocking the door. So let me first explain what is going on over here, like why does this whole thing happen. Okay, so let's look at it again. When the current is switched on, like this, we see that the current goes through this solenoid. And when it goes through the solenoid, okay, and there is a metal bar inside. This whole thing is an electromagnet. So now we use our right hand grip rule. Okay, so we see that the lines, okay, they are coming up. So in this case, all right, okay, I know you cannot see it, but it's coming up in this case. So when it's when it's going up, so when it's going up, it will be like this, right? It's going up. So when it's going up, all right, for me, because the camera is flipped, okay, so you'll be pointing over here. Okay, so right now the camera is behind the diagram, so that's why you cannot see it properly. But right now, if you were to do your right hand grip rule correctly, you will see that the north pole is at P and the south pole is at Q. Okay, so when there is current flowing through the solenoid, P will become a north pole and Q will be a south pole. Now when this happens, it will attract the iron bolt, okay, towards it. Now when you turn off, so this explains the first one. When you turn off the current stops flowing. Now because current stops flowing, what happens is that this will stop being an electromagnet, and this iron bolt, which was initially here, because initially it was being attracted by the electromagnet. Okay, now when you turn off, this spring will then pull it back, okay, to its original position. Okay, you'll pull it back to its original position like this. Okay, that's why when you pull it back, it will pull it back to its original position, unlocking the door. So this is actually what's happening in this question. Okay, so let's look at each question part by part. Part A, state the magnetic polarity. Now, what is magnetic polarity? I realize that many of you do not understand what this is. Magnetic polarity is just the poles. The poles at Q. So in this case, the magnetic polarity at Q is the pole. So just now we said that P is the north pole, Q is the south pole. What is the pole at Q? It is the south pole. So this is the answer, just south pole. Okay, the magnetic polarity at Q is the south pole. Now, part B, explain why the bolt is attracted to the electromagnet when the switch is closed. Now, I've already explained it. Okay, so let's try again. When the switch is closed, so we explain everything step by step, okay, or we explain everything one action at a time. So when the switch is closed, the switch is closed, current flows through the electromagnet. Okay, the electromagnet. Okay, so when current flows through the electromagnet, P becomes the north pole. Okay, when current flows through electromagnet, P becomes the north pole. Now, when this happens, okay, the iron bolt will become an induced magnet. Okay, so the iron bolt will become an induced magnet, okay, and be attracted to the electromagnet. Okay, and that's how the bolt is attracted. Okay, so what are the points here that are being raised? Okay, the first point, when the switch is closed, current flows through the electromagnet. This gives you 1 point. Okay, when the switch is closed, the current flows through electromagnet. 1 point. Second, you are going to tell me that P becomes or rather the electromagnet becomes magnetized. Okay, it becomes electromagnet. P becomes the north pole. Okay, and the last one is I want you to tell me that the iron bolt becomes an induced magnet. Okay, and because it becomes an induced magnet, all right, and it'll be attracted to the electromagnet. Okay, so this is what I want to see, the 3 points. Now, some of you can also write. I will also give you marks if you said that when the iron bolt becomes an induced magnet, okay, you'll be attracted to the electromagnet. If you tell me about one side being about this side, the part which is closer to the electromagnet, some of you say that this side becomes the south pole, and because like poles attract, this thing will attract each other. Alright, so I will give you marks for that as well. Alright. Now, next one. Connections to the cell are reversed. So right now, in this case, just now, the current flows out from here. Okay. Now, what will happen when the polarity of the what happens if the cell is reversed? Now, what does it mean by the cell are reversed? The cell are reversed means that right now this here is plus, here is minus. If the cells were to be reversed, it would mean that it will become like this. So here is originally this the left side is originally longer, but when you reverse, this side will become shorter, this side will become longer. So instead, current flows out from here. Okay, so current instead will flow out from here. Okay, and instead it will go down. Now, if knowing that when the current flows in the opposite direction, if you were to use your right hand grip rule again, just now Q was south pole, but now Q will be the north pole and P will be the south pole. Alright, so what happened to the polarity of the electromagnet? It will be, so just now P was north, now P is south, so it is reversed. Okay, so it will be, so to make everything very clear, you can just say that P, which is originally the north pole, will become the south pole. Okay, so it is reversed. It is switched. So P, the polarities of P and Q will be switched. So remember, polarity means what the poles will be. Okay, suggest two ways which the strength of the electromagnet may be increased. The first way is to increase the number of coils, the number of turns on an electromagnet. Okay, the number two is to increase the current flowing through the electromagnet. Okay, so these are the two ways. Electromagnet, you either want to increase the number of turns. When you increase the number of turns, the electromagnet becomes stronger. Or if you increase the amount of current, the electromagnet also becomes stronger. Okay? Now, last question, alright? Draw the magnetic field lines around the wire. Now, some of you drew this. Okay, I think there's quite a handful of you drew this. This is not a magnetic field. This is the electric field. This is wrong. This is the electric field. This is the electric field of a positive charge. Okay, this is the electric field of a positive charge, not the electric field, not the magnetic field. Okay, so when this is a plus, this is how the electric field will look like. Now magnetic field, this is the one whereby again we also use our right hand grip rule. So in this case, the current is coming out of the page. Okay, so because it's coming out of the page, alright, and then when you draw it, it'll be like this. Okay, the first two are, okay, the first circle that you draw must be very close. Okay, so because it's coming out of the page, you'll rotate anti-clockwise. The second one also very close, and then the third one you want to draw it very far apart. Okay, and you put in all the arrows. Okay, so that's how you can draw this. Make sure none of the field lines overlap and the distances gets larger and larger. Okay, now next one. Draw on figure 7.1 the direction of the wire. The direction of the wire will move if the current flows from A to B. Now if the current flows from A to B like this. Okay, so first one is the thumb, then there is the index finger, and there is the middle finger. Okay, so the thumb is the motion or the force. Okay, the index finger, this one, okay, thumb, the index finger, this will be the field. And last one, the middle finger, will be the current. Okay, so we want to know what is the direction of the force. So let's start by looking at the current. Let's look at the field. The field is from north to south here, like this. So we point it like this, okay, north to south. Alright, after that, the current will go from A, which is on the inside, to B. So this should be the other way around. Okay, so this will be pointing from north to south. The current is the other way, A to B, right? So this will mean that, if I'm not mistaken, many of your questions, okay, so it's flowing from A to B. Okay, wrong, sorry. I think in your question, in your paper, this is not A to B, this is B to A. Okay, here was B to A. Alright, so if it's B to A, then the current will be flowing down like this from B to A. Then same thing, you use your finger from north to south, and then from north to south and B to A. And this way, the direction of the field, the direction of the force will be pointing upwards. Okay, so this is how you can draw it. This is the direction of the force, it will be pointing upwards. Now the last one, explain the change in the balance reading when the current flows from point A to B. Now when it's the other way around, when it's the other way around, north to south, okay, and the current will flow inwards, okay, inwards, which is A to B, you will discover that the force will be pushing downwards. So we need to say that when current flows from A to B, the wire will be pushed downwards by the magnet. Okay. Due to when the current flows from A to B, the wire will be okay. Actually, I've written the answer here already. You just copy this, okay? Using Fleming's left-hand rule, okay, the force acts downwards on the conductor or on the wire, okay? Here's on the wire. This causes an increase in the balance reading. Okay, when using Fleming's left-hand rule, the force acts downwards on the wire, and this causes an increase in the balance of reading. So you can use this. So you need to tell me using the Fleming's left-hand rule. Then you can determine the direction. Okay, the keyword is downwards. Okay, and this causes an increase in the balance reading. Because when the wire is being pushed downwards, okay, we can see over here, when the wire is being pushed, if this wire was being pushed downwards, it will push against these two blocks. Right, be pushed against these two wooden blocks. This first wooden block, second wooden block. So if the wire was pushed downwards, it will push on the wooden block and it will increase the reading on the scale. Okay. Now, this is all. I have also set up a Padlet. If you have any questions, you can post your questions on the Padlet. Okay, and I will answer the questions to the best of my ability. There is no name on the Padlet, so anyone can post any questions that they have on any of the physics topics. Okay, so if you have any questions on the physics topics, you can post your questions there, right? There will not be no name, your name will not be reflected. So this way you can ask your question at ease. Okay, yeah, I think I've come to the end. All right, I will see you all next lesson. All right, bye.